Hi! So this is the first video for Math 1105 on inverses of functions. So in this video, we're going to learn all about inverses, how to tell if a function has an inverse that is also a function. And then in the next video, we will actually find inverse functions. So the first thing we'll talk about is we'll remind ourselves of what a relation is. So at the very beginning of the semester, we learned that a relation is a set of ordered pairs, and we can look at the set of ordered pairs in several different ways. One way that we looked at it was just as a list. Okay. So that set of ordered pairs right there, just written as a list of ordered pairs, counts as a relation. There is an x coordinate, there is a y coordinate, and we can think of it as almost the x maps to the y. So whenever we're talking about an inverse relation is going to map the same coordinates to one another, but in the opposite direction. So if you want to think of this relation, we can call it capital R, as 1 is mapped to 2, 3 is mapped to 8, 9 is mapped to 7. The inverse relation, which we write R with a little -1 up there, and it almost looks like an exponent, and it really is not an exponent. So be careful with it. It is not the same as 1 over R, like a negative exponent would do. It's just the notation for an inverse. So what the inverse relation does is it's just going to reverse that operation, or whatever operation it is. So 1 gets mapped to 2 in the relation, 2 is going to get mapped to 1 in the inverse. 3 gets mapped to 8. In the inverse, 8 is going to get sent back to 3. 9 gets sent to 7. In the inverse, 7 is going to get sent back to 9. So if we're just looking at a relation as a list of ordered pairs, finding the inverse relation is really quick. You're really just reversing the x and y coordinates. So if you're looking at the blanks on your notes, if you want to fill those in, you don't really have to. But the relation, the inverse of a relation reverses the actions of the relation. The inverse of the relation R is written R with a little -1. And a relation is just a set of ordered pairs. So to reverse the operations of a relation, we can just reverse the coordinate order. And that's all we did. We did a quick example here. Okay, so we'll do that first example that we have written in the notes just to kind of get the hang of what we're doing if we're given a list of ordered pairs. So let's say we've got the relation that's written in the notes. Our ordered pairs are 4, -1, -3, 2, and I ran out of room, 0, 5. Okay, so there's our relation R. We don't know how we get from x to y. Doesn't really matter. We just have a list of ordered pairs. So to find the inverse relation, first of all, we're going to call it the inverse notation R -1. Again, all we're going to do is reverse the action. So the relation R takes 4 and takes it to -1. Inverse is going to take -1 back to 4. -3 gets sent to 2. 2 is going to get sent back to -3. 0 gets sent to 5. 5 is going to get sent back to 0. So whenever you're finding the inverse of a relation, if it's given to you just as a set of ordered pairs, really simple. Our coordinates just get swapped. Okay, it's also pretty simple if you have a relation as an equation with two variables in it. So we decided this before, that something like 3x equals y squared plus 4 counts as a relation. Because if we wanted to, we could make ourselves a table with x's and y's, choose some values of x, solve for y, and we would get a list of ordered pairs here. Okay, we haven't ever graphed anything like this before, but it does count as a relation because we could list ordered pairs. There'd be infinitely many, but we could do it. So it counts as a relation. So if this is the relation given by that equation, So we'll just call it R with a colon. Whenever we have a list of ordered pairs, we just swap the order of the coordinates. If you have a relation given to you by an equation in two variables, you're just going to swap the variables that represent those coordinates. All right, so if that's R, our inverse is just going to be swapping these letters, really. So instead of 3x equals y squared plus 4, we're going to have 3y equals x squared plus 4. Done. X and y switch places. That's it. So if it's given to you as an equation in two variables, we find the inverse relation just by swapping the letters, really swapping the coordinates, but for every single coordinate you could possibly have. Notice though that everything else stayed the same in the equation. Only the letters changed. Okay, let's do another one like that. And this next one, I actually made a mistake in the notes. It should be 3x to the fourth minus y squared equals 15. The way I wrote it is not a very interesting problem. It's not an equation in two variables either. All right, so we have this equation in two variables. We have x and y. If we wanted to, we could choose some values for x and get some values for y in return, but we're not going to do that. We're going to find the relation that reverses this, the inverse relation. So we do that by swapping the coordinates, but we want to do it for every possible coordinate pair we could get. So instead of an x to the fourth, we're going to have a y to the fourth. Instead of a y squared, we're going to have an x squared. Everything else in the equation stays exactly the same. So what this would do is if you were given this xy table, or if you made an xy table for like 5 values of x here, and you chose the same values of y here, you would have the same ordered pairs just in the opposite order. So what swapping these coordinates does is it just swaps the coordinates for all of the ordered pairs in your relation, which is exactly what we want to do. Okay, so far we haven't used the word function, and that was on purpose because only certain functions have inverses that are also functions. So every function has an inverse relation. Right? I mean, we just showed that. To find an inverse relation is really simple. Swap the x and y coordinates and you're done. That's not a guarantee, though, that what you get in return is a function, even if what you start with is a function. So let's look real quick at some notation. So first of all, if we have a function called f of x, we write its inverse like that. All right, so same notation as we saw with the relation, only this time it's on the name of the function f. So we've got this little -1 up there. All right, what we want to keep in mind is that this is not an exponent. So you are not allowed to just flip the function over and find this inverse. That's not how it works. It definitely looks like an exponent that would turn something over, would reciprocate it, but it's not. It's the same notation for a different thing. Unfortunately, that happens a lot in math. This is one of those places. So let's talk about how we know, just from the original function, that if we were to take its inverse, if we were to swap the x and y coordinates, we would get a function in return. So what we need to remember is what it means to be a function. Okay. So let's look at this function, and we will remind ourselves how we know it is a function. Okay, so this one's just a list of ordered pairs. We know there are a lot of ways that we can talk about functions. One of them is just as a relation. The way we know this thing is a function is because the definition of a function tells us for every x coordinate, there is one and only one y paired with it. So if we go coordinate by coordinate, 4 as an x coordinate is paired with 1, and 4 as an x coordinate never happens again. Same thing with 3. It's paired with 7, and 3 is not an x coordinate ever again because it is only paired with 7. 5 is only paired with 0, 6 is only paired with 2. That's how we know this is a function. Now let's find its inverse. we know how to find the inverse of a relation. We just swap the coordinates. So we're going to have the coordinates 1, 4, 7, 3, 0, 5, 2, 6. Now let's look at it. Is this still a function? When the coordinates are swapped, is it still a function? Well, if we look at our x coordinates, they are paired with one and only one y coordinate. So this function has an inverse that is also a function. Okay, let's do another example. This is our first example. Here's our other example, and I'm going to try to write them on the same board here, or on the, before I erase the board, I want to write both of them so we can compare them. So here are the coordinates to the second function. 2, 5, 9, 4, 3, 5, 1, 0. Okay, let's remember what a function is and convince ourselves that this is also a function. And let's put a colon here, that's probably better. So 2 as an x coordinate is paired with 5, and 2 is not paired with any other y coordinate. 9 is paired with 4 and only 4. 3 is paired with 5 and only 5. 1 is paired with 0 and only 0. Okay, remember that this repeating y coordinate here is not a big deal if we're talking about something being a function. What we're most interested in is a repeating x coordinate. And since we don't have any repeating x coordinates, what we're looking at here is a function. Let's look at its inverse though. We just brought up this repeating 5 and how nobody cares since it's a repeating y coordinate and that doesn't stop something from being a function. But once we take the inverse of a function, that repeating y coordinate that didn't make any difference before is now suddenly a repeating x coordinate. And that's bad news whenever we're talking about something being a function. So this was a function, its inverse is not a function. And we kind of alluded to it just a second ago. The thing we're looking for here, whenever we're trying to decide if something is a function, we decided a long time ago that we can't have a repeating x coordinate. That's what makes something a function. But now if we're talking about an inverse function, we need it not to have a repeating x coordinate, and whenever we switch the order, we also need to not have a repeating x coordinate. So we're looking for a function that has no repeating x coordinates and no repeating y coordinates. That way, no matter what order the ordered pairs are in, we still have a function. So the types of functions we're looking for that have an inverse that is also a function are called one-to-one functions. So one-to-one functions have inverses that are functions. So every function has an inverse relation. It's just that inverse isn't always a function. We're interested in finding the inverse function. So we're going to be working with functions that are one-to-one, meaning no repeating x, no repeating y. For every x, there's one y, and for every y, there's one x. Okay. So whenever we were looking at functions, we were most interested in repeating x coordinates because that's what told us if we had something that was not a function, right? We could draw a vertical line through it. That told us if we had any repeating x coordinates, that told us it was not a function. Well, now we need something that passes this test and also doesn't have any repeating y coordinates. So we're going to use something called the horizontal line test. It works exactly like the vertical line test, except first of all, it's a horizontal line that'll be used, and secondly, it tells us something different. So the vertical line test told us whether the graph represented a function. The horizontal line test tells us whether the graph represents a function whose inverse is also a function. So tells us whether or not it's one-to-one. basically whether the function has an inverse that is also a function. So this is as easy to use as the vertical line test. You can basically just look and know. So if we look at this graph, for instance, we're assuming this thing slowly grows and slowly decreases over here. We can't draw a horizontal line that is going to intersect this graph in more than one point, right? So this thing passes the horizontal line test, which means it is 1 to 1. Which means if we were to find its inverse, it would also be a function. Okay, let's look at this next one. This one obviously does not pass the horizontal line test because it can't even pass the x-axis test, right? It passes through the x-axis 3 times, which means we have 3 points that have 0 as a y-coordinate. Totally fine if we want to just determine if this is a function or not. It certainly is. But once we take the inverse of that and start swapping those coordinates around, the 3 repeating y-coordinates that nobody cared about suddenly become the 3 repeating x-coordinates that make it not a function. So this one fails the horizontal line test. It is not 1 to 1, which means if we were to take its inverse, we would have something that does not pass the vertical line test. Its inverse is not a function. So we'll pick up on this at the beginning of the next video when we will actually find inverse functions.